Okay, let's get started. How is that one? Thumbs up, down, middle? Okay, at least better than the first one? If we could stay above that line, I think we're golden. I think I told you this last week, but the way I have to curve this course is very specific as to ranges of how many A's, B's, C's, so on. So I am going to wait until finals time to post a specific curve, just because if I curve the quizzes now and give you grades on that, it'll just come out in your final grade. Where if I curve them too much, then I'll have to be very strict on the final, and it doesn't really help. So what I will do is post just those ranges of grades that I do have to abide by. So that will give you a feel. You can see like where you are compared to the average. Again, I really don't like this. I don't like the competitive type where the tops whatever percent gets an A. But it's not my choice. So for now, I'll just keep trying to give quizzes in this range where the average naturally is around an 80 or a little bit below that. Okay, so done with that. Today we're going to review a little bit of forces and momentum, do a couple example problems, and introduce a little bit of a new concept. But overall, this is more of a review and just making things more concrete. So forces, like we talked about last time, are vectors. They have a magnitude and a direction, and they're just pushes and pulls. They're things that change the motion of other things. Forces change the motion of things. And it's very important that it's a change. So if something has a constant motion, its momentum is constant, no matter if it's a very high momentum or zero, positive, negative. If it's constant, you don't need a force to do it. You only need a force to change it. So if F net is 0, the motion of an object does not change. If it is not 0, then the motion does change. Important here that I put F net, right? If there's multiple forces acting on an object, but they all cancel out to 0, its motion or its momentum will also not change. So what is momentum? We use that as kind of the quantity to describe, or a vector quantity to describe our motion. It has both a magnitude and a direction as well. And it depends not just on the velocity, so its magnitude and direction, speed and where it's going, but also the mass of the object. This brings in the concept of inertia, which is just how hard it is to move something, how hard it is to stop it. Heavy things are hard to move, and when they're moving, they're hard to stop. The opposite goes for things that are lighter. So heavier objects have more momentum, and objects that are moving faster have more momentum as well. Impulse is when forces change the momentum of objects. So we saw here, delta P is related to F net by multiplying it by the change in time. So the longer we apply a force, the more impulse we deliver to an object, the more its momentum changes. When you have just two vectors that are equal to each other, multiplied by a scalar, that means a scalar means something without a direction. Delta P and F net are in the same direction. So whatever direction my F net is, that is the direction the momentum of the object will change. This J net is called impulse. It just describes either of those two things. Forces over time deliver an impulse. Impulses change momentum. I don't think J is really all that important. It's just the symbol that we use, but the meatier, more informative things are the force over time causing a change in momentum of an object. Just that the thing that's delivered, this thing that has units of kilograms, meters per second, is impulse. So direction is very important to pay attention to, and also the magnitude of your momentum does not have to change in order for the momentum to change. Since it's a vector, we can change it by altering its magnitude or its direction, right? So even if if I'm moving 5 meters per second this way, and then some force is applied to me and I'm moving 5 meters per second this way, then my speed didn't change. The magnitude of my velocity and momentum did not change, but the direction did. So that still is a delta P, as we'll see a bit later. More about momentum, I said The top part, constant if F net equals 0. So a constant meaning delta P is 0. So just P initial equals P final. Doesn't mean either P initial or P final is 0, just that the difference between them is. We also have systems composed of a bunch of objects with their own momentum, in which case the total momentum is just the sum of all the individual ones. This is a vector equation. So whenever we have something like this, where we have a vector equals another vector, or the sum of them, or subtraction, or anything like that, we know that really this is kind of multiple equations in that we have an x and a y. So here I just wrote P total vector is P1 vector plus P2 vector, so on and so forth. But this means that P total x is P1x plus P2x, or P total y is P1y plus P2y, so on. You could do the same for 3 dimensions, 4 dimensions, whatever. We're going to stick to 2 dimensions in just a plane and the xy in this class. So vectors have these 2 dimensions. Yeah, and just kind of a restatement of above. A closed system is when the F net is 0, so our delta P total does not change. Very important there that individual objects can have a delta P, but they will all cancel out. They'll just exchange momentum instead of, the total will remain the same. For an open system, there is an F net, and so the sum of all the momenta of the objects can change. They can still exchange in between each other, but in addition to that, the total can be different if there is an F net. So let's do an example. This one's pretty simple math-wise, hopefully, but we haven't really worked out a problem together where we go all the way from a bunch of numbers, like forces, times, all the way to a velocity. So even further than the momentum, really describing the motion of an object. So I want to just work through this in detail. So we have an object here, it's at rest, so initial velocity, speed, momentum are all 0, and then 2 forces are applied to this object. One is to the right, 3 newtons to the right for 2 seconds, and one is down, -4 newtons in the y direction for 3 seconds. And we want to know, after both of these forces are applied, what is the magnitude and direction of the object's final velocity. Something to notice here, let's make a momentum chart. It's important with these, just like when we were doing fluid circuits and circuits and stuff, we have to decide our initial and our final when we want to calculate a delta. So in this case, it's over time, not position, but we still need to choose when's my initial time and when's my final. And the question asks, what is the magnitude and direction of the object's final velocity after both of the forces are applied? So that'll be my final. We don't care that one force happens and then the other. In fact, the order doesn't matter at all. They could happen at the same time. One could happen first, other way around. My final answer is still going to be the same because each force delivers some amount of impulse, and that adds to the object's momentum. And that's it. There's no, whether they're consecutive or simultaneous or anything doesn't matter. So my initial before either of them acts, and my final is after both of them are done acting. And the first thing I can write here is that my P initial is 0, because we're told that the object is initially at rest. So my V initial is 0, my initial momentum is 0. Then we have some delta P, and we know that delta P is not going to be 0, because there is a net force from these 2 forces here, and our net force is going to be the sum of our 2 forces, right? And then whatever direction F net is in, delta P will be in as well. All this is saying qualitatively is that we have a force and it's pushing on the object is going to go in that direction of that force. That's not always necessarily true if the object has some other initial motion, but if it's still and we act on it with a force, it's going to move in that direction. So let's add these 2 vectors together. I just did it qualitatively here, F1 plus F2, and we get some F net that is to the right and down. F1's to the right, F2's down, so the net is diagonally right and down. And so our P final is just 0 plus this delta P, and it's whatever impulse that was delivered by the F net. Momentum charts are never something that I will ask you for on an assessment. I think they're really useful. both to check your work and get started on your work, as we'll see, like we're using this as a jumping off point. But if you don't like them and you prefer to just start right with the equations, that's up to you. You will be asked for them in DL, but again, not on quizzes or the final. So the equations that we can write from this that we did graphically with the momentum chart are, delta P is F net delta T, right? And then beyond that, we know that our momentum, because we're asked for our final velocity, is equal to our mass times velocity. And because both of these are vector equations, that really means we have two of them, one for the x and one for the y. So completely separately, we have impulse in the x direction that gives it its x momentum, and then impulse in the y direction that gives it its y momentum, and then individual final velocities and momenta. So the thing we need here to calculate the delta p's in the individual directions is F net, which in this case we don't need to do any trig because we're already given the f's very conveniently in terms of their components. So these are simple to add. In the x direction we get 3 plus 0, so 3, and in the y direction we get 0 plus -4, so -4. That doesn't get much simpler than that when you're adding components together. So our F net is that down and to the right vector we saw before, and we can take that and plug it into each one of these individual delta P equations here. So let's start with the x direction. We know delta P is F net x, delta Px is F net x delta T. So we know the x component of the force is 3 newtons, positive, and it occurs for 2 seconds, like we see in the problem statement. So the impulse in the x direction is 6 kilograms meters per second. And then further than that, we also know that our P final is just our P initial plus delta P. P initial was 0, so our P final is just whatever that delta P was. This is really writing out laboriously a lot of stuff that the momentum chart showed us, but we know our P final is just going to be that same 6 kilogram meters per second in the x direction. And then we're not asked for the momentum, we're asked for the velocity, right? So we know that momentum is mass times velocity, and all of this is just in the x direction. So our velocity is just our momentum divided by our mass. So that's our 6 kilogram meters per second that we just found, divided by the 3 kilograms of the object, and we get its x velocity is 2 meters per second in the positive x direction. So this is only x, we're moving 2 meters per second here. And we can quickly see how mass affects this type of thing. So this 6 kilogram meters per second was only calculated using the force and the time. So this is the impulse, has nothing to do with that specific object. The mass is what determined how the object reacts to that force. If this was a really small object, so this was a really small mass, this would be a bigger speed, right? If I apply the same impulse to a tiny object, it's going to make it go a lot faster. If this was a huge mass, if this was 3 tons, then this would be a tiny speed. If I apply that same impulse to a huge object, it's just not going to move as fast. So we can see physically how the mass affects things. But anyway, our takeaway is final x velocity, 2 meters per second. Now let's do the y direction. Same set of steps. Delta py is F net y delta t. From what we're given, we find that's negative 12 kilogram meters per second, which is negative because F2 is pointing down. And then our P final is just the same as that delta P because we started at 0. So our P final is negative 12 kilogram meters per second. And then if we want to find our velocity in the y direction, we need to divide that by the mass. So negative 12 over 3, we get negative 4 meters per second in the y direction. So putting that together, we found our velocity vector has the components 2, negative 4. And if we draw that out, we can see it looks a lot like the force vectors, right? We said force, net force, goes in the same direction as delta P. And since this object started at 0, that delta P is just what momentum did we give it. And that momentum that we gave it is in the same direction as the force. So you can clearly see how we get from force pushes on something, it moves in that direction. Now we're not asked for the components, we're asked for the magnitude and the direction of this velocity. So for the magnitude, we know the Pythagorean theorem that the hypotenuse is the square root of the sum of the squares. So we get the square root of 2 squared plus negative 4 squared. Important that all the negatives turn into positives for the magnitude, right? Because it doesn't matter what direction this arrow is pointing when we're looking at the length. We only have positive length. So the answer comes out to around 4.5 meters per second for our magnitude. For the direction, we need to do a little trig. The way I've labeled it here, I'm saying theta is the angle below the x-axis, or south of east. And so the opposite is y, the adjacent is x. So we know tan theta is going to be our y over x, opposite over adjacent, which here is 4 over 2. When doing the angle, I also got rid of the negative. The reason being, I think it's just easier to find the angle, be clear about where I was trying to find it, and state that. So in this case, it's 63.4 degrees south of east. It is possible to use trig and keep the negative signs in there. You can have trig functions of negative numbers, all this stuff, angles bigger than 90 degrees. I think it's much easier, and all the examples in this class, we will just keep everything positive, lengths, angles, and between 0 and 90 degrees. That way our trig functions are nice and simple, but that just means it's very important that you're always specific about what your angle is referring to. So in this case, the way I've labeled it, 63.4 degrees south of east. I could have also labeled the angle with respect to the negative y-axis, or east of south, in which case, instead of 4 over 2, I get 2 over 4, because now the x component is my opposite and the y is my adjacent, and so I get a different angle, 36.6, which happens to be the complement of the other angle. So those two add up to 90, which is what we expect, right? Because adding together, then we're just finding the angle between the negative y-axis and the positive x-axis. So those should be 90. And both of these answers are equally right. 36.6 degrees east of south, or, I don't know where I got lost here, or 63.4 degrees south of east. They both mean the same thing. So let's take a step back into just more qualitative assessment of this stuff. We have a ball. It's initially moving upward, and then it explodes and splits up into 3 pieces that are moving in different directions. We want to know which one of these final situations pictured here does not conserve momentum. So if this ball is moving upward and it explodes, which one of these final pictures where these are all momentum arrows is not possible? So I'll leave this up for a little bit. So I'll give you a little bit of a hint if you're not sure where to get started with this one. The thing we're looking for is conservation of momentum. The reason being there's no external force. There is some explosion that sends these pieces away, but it's kind of similar to like if I was floating in space and I throw a ball to the right, I'm going to move to the left. Right? If I deliver an impulse to that ball and there's no external force, then I have to go the opposite way. The reason that doesn't happen when I'm standing on the ground and I throw something is because my feet are on the floor, and there's like the floor is keeping me from moving. But that's an external force. There's no external force on the ball, so my initial momentum has to be the same as my total final momentum. So which one of these pictures, if I add up the 3 momenta, does not give me a total that is the same as my initial? I'll give you a little bit longer to think about it. All right. Let's see how we did. Pretty good, but a little bit split. So let's work through these together real quick. So we know we're looking to conserve momentum. So the total momentum of all three pieces must be just one arrow pointing up. For A, left and right cancel out. So that's fine, and then we're just left with a single up arrow. That works. For C, we also have a left and right pointing out, so those the X components cancel out. And then each one has a little bit of an up component added with the third up component on top. That also works out to just some total arrow pointing up. E is very similar to C, except the top arrow is now pointing down, but each individual one on the left and right are pointing up. So it seems like something that you wouldn't be able to do without getting really precise with a ruler, but we can, I think it's easier to think about if we completely split it up into X and Y. So in the X direction, the two components on the sides have equal and opposite components, right? The one on the left has some left component, the one on the right has some right, those cancel. So our X component is 0. That's good, that's what we were looking for. In the Y direction, our Y component is just however much of these arrows is pointing up. And that happens to be the same amount, the same magnitude as the amount this arrow in the middle is pointing down. So if we have 2 going up and 1 going down, and they're all the same length in the Y direction, the net is going to be just 1 up. So this one actually does fit our initial total momentum as well. We get the net up. D is just 3 arrows pointing up. Those all add together and we get an up arrow. B is the right answer. That one is impossible. Unlike E, where there's 2 pointing up and 1 pointing down, now we have 2 pointing down and 1 pointing up. So our net is 1 down. The X still does cancel, so we're left with a momentum that is only in the Y direction. But yeah, our net Y is down, so the momentum is not conserved. In order for B to be possible, we would need some net force to push down on the object, which we do not have. Okay, so now let's do an example of momentum of a collision. And there's going to be a lot of concepts that come into this one, but it'll be practice with momentum charts, using values, and interpreting all of that. So here's our example. I spilled chocolate milk over some quizzes that I was grading, so I couldn't read them. As a result, I had some angry students, and so those students threw eggs at me while I was rollerblading to class. I know that my mass is 60 kilograms, and I was moving at 5 meters per second in the positive X direction. And that each egg, there were 3 of them, is 0.25 kilograms, and it's moving at 20 meters per second in the negative X direction. So we're only dealing with one dimension here, forward and backwards, positive X and negative X. I'm moving one way, 3 eggs hit me and slow me down. And I want to know how much those 3 eggs hitting me, slow me down. So the things that we can take from this problem statement so far, the system is going to be me and the 3 eggs. I wasn't super specific about it here, but no external force. So we'll say no friction, air resistance, anything like that. So it's just me exchanging momentum with the eggs. Right. And so since there's no external force, our total change in momentum between me and the 3 eggs is 0. So let's make a momentum chart, and the first thing we can fill in is that our total delta P is 0. If you read no external force, you can always pop that 0 in the total change in momentum column. What else can we fill out? Well, we know the initial conditions of this problem, right? We know my mass and my velocity, so I can draw my initial momentum arrow, which is in the positive X direction and has some magnitude, and then I can also write the eggs' initial momentum. In this case, I combine them all into a single row because there are 3 of the exact same thing. Right? They all have the same initial and final conditions. They all have the same mass. So just like before when we had 2 forces acting and we just considered them together as a net, I'm going to do the same thing, combine them into one net egg because we don't care about each individual collision. We just care about the total. So in total, we have 3 times 0.25 kilograms, so 0.75 kilograms, and velocity of negative 20 meters per second. So this arrow is pointing in the opposite direction. And we'll prove this on the next slide, I think. But the arrow is much shorter because the magnitude of 3 times 0.25 times 20 is much smaller than 60 times 5. So even though I'm moving much slower than the eggs, I weigh so much more than them that my momentum is still much greater. So now if I have the components of my initial total momentum, I can just add those up. And my total initial momentum is just a momentum arrow that's slightly shorter than my initials. Right? So I have some here. If I add these two vectors together, this one's going to take a little bit off of that one, and I get some initial momentum in the positive x direction. The next obvious thing I can do, initial momentum, delta p is 0, so my total final must be the same as my total initial, right? And all this is saying is that any change in momentum is an exchange between me and the eggs. The net has to be 0. To move on from here, so we've done all the quote-unquote obvious stuff. Now there's no, if we consider each one of these as like a little equation, we can't really go any further without some more information, because both of these, now we have 2 things missing from each equation. So the key thing we need to realize is that the eggs stick to me. Well, I didn't say that, but I guess I'm telling us to assume that here. When the eggs hit me and crack, they stay attached. So if I'm moving and an egg hits me, we now have the same final velocity, right? So when the eggs hit me, my final velocity and their final velocity becomes the same. I'm rolling, they hit me, and now we're stuck together. That's a key, it's like a type of keyword. Like before when you saw things like ignore friction or something like that, or closed system, all these things that you might read in a problem statement, when things stick together, a key thing that you need to pull from that is that their velocity is now the same. And that's, we'll see in this problem, but always very important to solving that problem. So since our final velocities are the same, I can now say that for our final momenta, each individual momentum, mine is my final velocity times my mass, the eggs is the same, their final velocity times my mass, but these velocities, their final velocities are now the same. So this isn't really important to solving the problem, but if we take the ratio of those 2 things, so my momentum over the egg's momentum, the velocities cancel because VF, VF, they're the same, so I just get the ratio of our momenta is just the ratio of our masses. And if on the top I have my mass, on the bottom I have the 3 eggs mass, and it's a factor of 80. So my momentum is 80 times bigger than that of the eggs in our final state when we're moving together. So now we're getting somewhere. We go back to our momentum chart. We know this is our total. We know my momentum and the egg's momentum are moving in the same direction, right? Because we're attached. We have the same velocity. The momenta are going to be different lengths because we have different masses. And we found that my momentum is about 80 times larger in magnitude than the eggs. So we could, using those things, we could technically write a system of equations to solve it. But while we're just doing this graphically right now, if I know that they both are pointing in the same direction, they both better be pointing in this direction of the total, and mine is going to be much larger than that of the eggs, right? So they have some tiny arrow, and I have some bigger one. These 2 add to the total. And this represents me with eggs all over my chest, moving forward all together. Clearly, this arrow is not 80 times smaller than this one, but we don't need to be that specific when we're doing momentum charts. Momentum charts are more for the qualitative picture of something, so you're not going to have like 6 rows and have all these different lengths of momentums that you have to use a ruler to keep track of. In general, you need like 1 type of long arrow, a medium one, and a short one, or something like that. As long as you know when 2 things should add up and maybe change direction, or add up and be longer than each individual one, those, like logically it has to make sense, but if this one is supposed to be 80 times this one, you don't need this to be microscopic. You can just say, okay, I'm going to draw this arrow a lot smaller, and it will still help us solve the problem all the same. The same goes for like direction and stuff. We don't need to use protractors to draw stuff, but if one thing's pointing up, the other thing's pointing to the right, our net should be vaguely pointing up and to the right. Anyway, now that we have these two pieces, we can fill in the rest of our momentum chart, because now we have equations with only one thing missing. So if my initial is this arrow here, my final is a slightly shorter arrow, my delta P is just the difference in the opposite direction of either one. It just takes some of my momentum away. So qualitatively, that just means I was skating forward, I got hit by the eggs, and that slowed me down a little bit. The eggs, on the other hand, changed direction. They were coming toward me, and then after they hit me, they're now moving in the opposite direction of their initial travel. Now they're moving with me. So their change in momentum has to not only reverse their initial, but then give them some more final momentum in the other direction. So this arrow has to be longer than either of these two. If we wanted to be very meticulous and use vector addition physically to do this, it would be, if we want to find our delta P, we do P final minus P initial. So here's our P final. Our negative P initial would be facing this way as well, so it'd be their two magnitudes added together. Another way we could have seen that is, if this is my momentum change, the momentum change of the egg needs to be equal and opposite, right? Whatever momentum they gave to me and slowed me down, I need to give to them in the opposite direction so that my total is 0. So now this is really 6 equations that we have here. We have an initial delta, initial during, I guess, is our delta, and final that describes the system. We also have an initial delta and final for me, the eggs, and the total separately. And we can use those together to find what we're looking for. So let's go ahead and start with our bottom row, which is a very easy equation. That's just the P total initial is, oh, sorry, I guess that's not the bottom row. We want to figure this first column out first. What is this P total initial? So we know my initial and the egg's initial, right? That's listed in the problem statement. I'm told my mass and my velocity. Same thing with the eggs. So I can just plug in here that my initial momentum is my mass times my 5 kilogram velocity plus the egg's mass. And here I have a factor of 3 because there's 3 of them, but they're all doing the same thing. Their mass and their velocity, which is negative because it is opposite my velocity. And I get a total of 285 kilogram meters per second. So that is the total momentum in the system when I was moving forward and the eggs were moving opposite me. And now we can move on to this bottom row that I was talking about. This just tells us that our P initial equals our P final, right? Because our delta P was 0. So whatever this total initial momentum that I solved for is also our final total momentum. And now we can use what we're going for is my final momentum, I mean eventually velocity, but what we're looking for is my final motion. How much did the egg slow me down? So if I have this final momentum that's total, I can write that out as whatever this last column's equation would be, this P final column, where my P total final is just the sum of my final momentum, is 60 kilograms times that VF, plus the egg's final momentum, which is their mass times that final momentum. And now I have an equation that will just let me solve for what this final velocity is. And again, it was super important for us to recognize that these two VFs, that my velocity and the egg's velocity, were the same. Because they stick together, this VF's the same. If these were two different velocities, we wouldn't have enough information to solve the problem, right? Because then we have one equation, 2 unknowns, we're stuck. But since we only have one unknown, we can solve. So VF ends up being this 285 divided by our total mass. So I kind of skipped a step here, but if I factored out this final velocity, then I just get my 285 is equal to VF, total, the final velocity, times 60 kilograms plus the egg's mass, right? So a way of seeing that is just, well, we're all one object now. The eggs are stuck to me, and we're traveling together. So the final momentum can be thought of as just our velocity times our total mass, me and the eggs. which is this here. So if I want the velocity, I'll just divide the momentum by the mass. 285 over the total mass, which is 60 kilograms, plus this 0.75. And we get a final velocity of like 4.7 meters per second, which I think makes sense, right? I was moving 5 meters per second to start with, and then the eggs hit me and slowed me down a bit. On the egg side of things, the eggs were moving negative 20 meters per second toward me, and then they hit me and stuck and slowed, like, so the magnitude of their speed reduced, right? They were moving really fast toward me, and now they're moving slowly, but the direction flipped around. So now they are moving at this slightly slower velocity forward. So to summarize, upon the collision, the eggs and I exchanged momentum. So our momentum changes were equal and opposite. They add to 0. Caused my speed to reduce, and the eggs' speed to, well, the speed decreased, but the direction changed entirely. So the velocity for them flipped signs, and its magnitude shrank. And then afterwards, we were traveling together with the same speed. And the total momentum was the same as the initial. So that's our whole picture as far as the momentum goes, and we used it to solve for velocity. Another way to think about it is like the eggs delivered some impulse to me. I delivered equal and opposite impulse to the eggs. All right, so now let's introduce not really a new concept, but use it in a different way. Let's look at the kinetic energy. So we did this, I think you've done this in 7A, and we did this kind of with Bernoulli's too. But instead of now talking about density, we're just going to go back to good old-fashioned kinetic energy, 1/2 mv squared. So this is the kinetic energy of an object with mass m moving with speed v. So what's our initial kinetic energy? Well, it's just going to be the sum of the kinetic energy of all the parts. So it's the sum of my kinetic energy, my mass times my speed squared, plus the same thing for the eggs. So if we plug that in, we get 1/2 times 60 kilograms times 5 squared. That's my initial kinetic energy. Very similar for the eggs, except I added this factor of 3, their mass, because there's 3 of them. So you could either think of this as 3 terms of 1/2 mv squared, or us just considering the mass to be 3 times as big because there's 3 eggs. It doesn't really matter. We just know that each one delivers a bit of impulse and they add together. In this case, each one has some kinetic energy and they add together. Another thing to notice, negative 20 meters per second gets squared and becomes positive. So when we're dealing with kinetic energy, direction or negative signs do not matter. The reason being, something traveling in the positive x direction with 5 meters per second has the exact same kinetic energy as one traveling in the negative x direction with 5 meters per second. Same thing as the one with the positive y direction and the positive x direction. Like, direction does not matter for kinetic energy. So when we're finding this v for kinetic energy, it should always be, well, it doesn't matter if we put a negative number in there. It'll get squared and become positive, but we always need to use the magnitude. So if I'm given a velocity vector with an x and a y component, I need to find the magnitude of that to plug in for my speed, because individually they don't work. And I can't just do like x kinetic energy plus y kinetic energy. That does not add up the same. So this is similar to like in Bernoulli's. It was very specific that we did delta v squared, not delta v squared. Same type of thing. Anyway, for speed we put in a magnitude, and then our result is that our total kinetic energy is 900 joules. So I have some kinetic energy, eggs do. That's our total. Great. So now what about our final? Our final, same thing. We'll just add up whatever the final kinetic energies are for me and the eggs. For me, it's now instead of 5 meters per second, we have 4.69. Now for the eggs, instead of negative 20, we also have 4.69 because now we're stuck together. We have the same V final, and our result is our total is only 668-ish joules. So our final is much less than our initial. We lost a bunch of kinetic energy. This type of collision is called an inelastic collision. So collisions in which you lose kinetic energy are called inelastic. we didn't lose energy. Like, we know energy isn't created or destroyed, but it gets dissipated into other types of energy, which is something familiar that we've seen so far. It could be thermal, things heat up. Sound, if you hear a collision, it took energy to make that sound wave. So that's where some of it went. So in reality, most collisions, except on a subatomic level, are at least somewhat inelastic, and then some energy is dissipated. But yeah, we can assume a lot of things are. Like a tennis ball bouncing off the ground, doesn't lose much kinetic energy. So, well, let's move on to what the opposite of an inelastic collision is elastic. I want to make a note, this is backwards. All of the writing is correct, but these two first top lines are mixed up. I'll fix this when I finish this lecture and post it again. But for inelastic, initial and final are not the same. So that first line on the inelastic side should be not equal to, and for elastic, they are equal. So kinetic energy does stay the same for elastic collisions. So sorry about the typo, but inelastic, they lose kinetic energy. Elastic, they remain, the kinetic energy is retained. So they don't dissipate any. So what does that look like? Inelastic collisions, like we said, dissipated as sound or thermal energy or something like that. It happens whenever something sticks together. So when things stick together, that's some absorbing of energy for them to stick. It's just a bunch of algebra, not really interesting, but you can actually prove if I demand that two objects stick together in a collision, that their final velocities are the same, it's actually impossible to conserve kinetic energy and have a collision. So if they stick together, I already know it's inelastic. But it can also occur when they bounce a little bit, right? Like, just because an object does bounce off something, it still can dissipate a bit of energy. So things can be completely inelastic and stick together, or just partially inelastic, where they bounce off but still lose a bit of energy. How do we check? Well, calculate the initial, calculate the final. If they're not the same, some energy was lost, and it's at least partially inelastic. Elastic, again, this is wrong, it's when initial and final kinetic energy are the same, is when, I think the term is kind of intuitive. Elastic, you think of like stretchy, bouncy. When they collide, they lose no energy. So they bounce off each other. And then, yeah, it happens when they bounce off each other and lose no energy. That's perfectly elastic. No energy is lost. Like I said, this isn't super physical for macroscopic collisions. All the collisions that we see usually make some sort of noise, even if it's a very tiny noise and is a tiny percentage of the energy involved in the collision, it's still a little bit. So technically, it's a little bit inelastic. But for this case, we can make a lot of assumptions. Like if I throw a tennis ball at a wall, I'll probably model that as elastic because there's very little energy lost. It bounces really easily and efficiently. If I throw a ball of clay at the wall, same mass, same initial velocity, it's going to stick, and we know it lost all of its kinetic energy, right? That you can see the perfectly inelastic, where it went from whatever kinetic energy it had to zero. That would be inelastic. So, and like we saw with the previous problem with the eggs, this can be a key in determining the behavior of a collision, right? When the eggs hit me, I wasn't able to solve that problem without knowing that they stuck to me, that the collision was inelastic, and that I could demand that the final velocities were the same. So the way you'll be asked this, or the way this will come into problems, a lot of times it will just be, is this collision elastic or inelastic? And for that, you can use qualitative clues, like if they do stick together, it has to be inelastic. But usually you have to prove it by solving. So even if objects bounce, we'd have to calculate, see if my initial kinetic energy matches my final. And that's how that would come in. You could also, I guess, use these as something to solve if I tell you that the kinetic energy is conserved or that the collision is elastic, then you would know something about their final velocities, and you could use that to plug in somewhere else. But what I'm trying to say is there's not too much more to this problem, or like to this concept. There's not really any new math. It's just calculating kinetic energies and comparing. Let's do a clicker question. We have a piece of garbage floating through space with some initial velocity in the y direction, and it hits the moon. The moon doesn't react, which just means it doesn't move, right? So we'll just consider the moon as huge and immobile, so it doesn't move. The object hits it, and then after the collision, it has a new velocity that is to the right and down with these specific components. So I want to know if the initial velocity is this, final velocity is that, was this an elastic collision, and then also is the momentum of this piece of garbage conserved. So take a sec for this one. You should probably write something out for this, or at least try to do it in your head. I'll give you a little bit longer. $15 more seconds. All right. So again, split on this one. That's all right. It's a new concept. So the correct answer is B, that it's elastic and momentum is not conserved. So if we plug in our initial kinetic energy, 1/2 mv squared, 1/2 m, and it's only in the y direction, so our speed is just 5 meters per second. For our final, we need to find the magnitude of the velocity, right? Get the speed. So we have to use both components. 3 squared plus 4 squared, square root of that, ends up also being 5. So we find that the speed stays the same, even though in the first case it's moving up, and in the second case it's moving down and to the right. The speed at which it's doing so is the same, and so its kinetic energy is the same. So it is elastic. When it hit the moon, it lost no energy. However, momentum is not conserved because there was a net force from the moon, an external force. And there's a lot in this problem, so it seemed pretty simple, but we had to decide that the system was just the piece of garbage because the moon does not move at all, right? It's just a stable piece. If we modeled the moon as just another object, right, then we know that the garbage gives some momentum to the moon gives some momentum to the garbage, and then momentum is conserved within that system, equal and opposite, some exchange. But in this case, we said the moon does not move. It's just like an external force, and so momentum is not conserved. I've always struggled a little bit with that way of stating things, but it's helpful to understand both sides of it. Momentum, so the way the world works is kind of backwards for how this answer makes it seem. In this case, we say the collision is elastic. That doesn't have to be true, right? Collisions can lose energy. In fact, they pretty much always do. Elastic collisions are pretty, they're not really applicable to a lot of physical systems if we're being really precise. On the other hand, momentum conservation is a rule, right? Conservation of kinetic energy doesn't exist. There's conservation of energy. Energy can change forms, though. So it doesn't have to stay kinetic. It can be kinetic, potential, voltage, whatever. So elastic versus inelastic, there's no rule about that. Momentum conservation is a rule in the world. There's a certain amount of momentum, and it stays the same. If we make the system the entire world, then or the universe, whatever, if that's our system, momentum is conserved within there. If there's no external force on the universe, then the total momentum in the universe is the same. The reason we use this language that momentum is not conserved, which sounds goofy, is that we have to define our system. And momentum can be not conserved within a system if there's a net external force. Right? So we can always extend the bounds of our system to include whatever the thing that was the external force. And in that case, it's no longer an external force. And now our delta P total is 0. So be careful about what you include in your system. If the object that is applying the force, we also care about its motion, then we probably want to include it in our system. Right? If I asked you how much the moon moved as a result of this, I would need to know more. I would need to know its mass, but I would also include it here and have no external force. In this case, since I told you the moon does not move, and I'm only interested in what the object's motion is, I only consider the object as part of the system. All right, that's all I have for today. Another quiz next week. I'll post details about that later today, and I'll see you next week.